Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. Students, I welcome you all to your Nexus Batch. And today, we are going to start with lecture number 8 based upon the chapter Chemical Bonding. Students, this is going to be the last session for this particular chapter, Chemical Bonding. I hope so. This chapter was quite clear to you and you are able to solve questions also and you are able to get the concept with regard to the chapter chemical bonding. Yes, everybody? So, students, let us proceed this session with a beautiful smile. As I have already told you, this is going to be your lecture number 8. So, what are the topics, ma'am, that we are going to cover in today's session? See, initially, we will be proceeding further with the molecular orbital theory that we have done in the previous class. In the previous session, students, I have already told you about molecular orbital theory, how to calculate electronic configuration, how to draw energy level diagrams, right, in various cases. Today, we'll be doing the part 2. That means we will be understanding about the molecules which have electrons more than 14. I have given you the general trend or the general order for the electronic configuration. But yes, today I will be doing on my own and letting you know how to do this. So you can match your answer with mine, right? Moving further, we will be understanding about bond order, right? About stability with regard to molecular orbital theory. We will be understanding how bonding molecular orbitals are created, how anti-bonding molecular orbitals are created through constructive interference, through destructive ones. We are going to understand that in depth. Moving further, we will be understanding about how sigma bond is created, how sigma star bond is created, how pi bond is created, how pi star is created. So we are going to understand this also in part number first. Now talking about part number second over here, students, what are we going to do? First of all, we'll be understanding about Fazan's rule. Okay, we'll be looking about the covalent character in the ionic compounds. We will understand that in depth as well. Moving further, I will explain you about the bond parameters such as bond length, bond order, bond dissociation energy, bond enthalpy that we refer to as lattice energy. Okay, all of these terms. Drago's rule, sorry. Okay, so all of these topics will be covered in the second part. Third part holds the hydrogen bonding, where we'll be understanding about what is hydrogen bonding and what are the types of hydrogen bonding. Clear, everybody? So let's proceed this session with a beautiful smile, everybody. Now we are going to start with the initial topic, that is molecular orbital theory. See, students, as per the molecular orbital theory, if I'll talk about, I have already explained you the concept where we had electrons less than 14. Now let's take a case where you have electrons more than 14. An example I've given you of O2 and I have given you this as a homework. So let's see your answer is matching mine or not. Okay, so in the case of oxygen, we know that total how many electrons are there? Total 8 electrons are there. And and it is basically how many oxygen atoms? 2. So this comes out to be how many electrons? 16 electrons, right? In order to fill 16 electrons, how we are going to start with? It is going to be sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2. Now, in the case of the ones which have more than 14 electrons, initially what will come over here? Initially, sigma 2pz will come. It holds 2 electron. Now, count the electron. 2 plus 2, 4. 4 plus 2, 6. 6 plus 2 is 8. 8 plus 2 is 10. Still, how many electrons are left? How many electrons? If you'll see over here, it is 4 plus 4, 8 plus 10. 6 electrons are left. Now, we'll move on to the pi 2px is equivalent to pi 2py. So 1, 1, 2, 2. Like this, you'll fill it. Now count the electrons. 2 plus 2, 4, 6, 8, 10, 12, 14. 2 electrons are left. Now it will move on to pi star 2px is equivalent to pi star 2py. You have to fill 2 electrons. So 1, 1 each. This is going to be the electronic configuration, students. If you have to draw basically the energy level diagram, let's write down this configuration over here so that we can draw it over there. Yeah. I have written the electronic configuration over here so that I can draw my energy level diagram for the case of O2 over here. See students, initially we very well know that if we have one oxygen atom, it has an atomic number 8. It is going to be 1s2, 2s2, 2p4, right everybody? So this is going to be your initial oxygen atom with 1s. This is another oxygen atom with 1s. Now they both are combining with each other, students. Right? So when two atomic orbitals combine with each other, they are going to form two molecular orbitals. This is going to be sigma 1s. This is going to be sigma star 1s. This is your bonding molecular orbital. This is your anti-bonding molecular orbital. AMO also in some times I've written, and I've written ABMO also. You can write ABMO, that will make you quite clear. Anti-bonding molecular orbital. Now moving on to the next one, we have 2s orbital of oxygen. We have another 2s orbital of oxygen. So when again two atomic orbitals combine with each other, they are going to form two molecular orbitals, students. So these are creating two molecular orbitals yet again. This is going to be sigma 2s and this is going to be sigma star 2s. Yes. Now comes the p orbital of oxygen atom. We very well know that there are three p orbitals. We have two oxygen atom, right? This is 2p orbital, this is 2p orbital. Each 2p orbital contains 4 electrons. So 1, 2, 3 and 4. 1, 2, 3 and 4. Now when they are going to combine with each other, they are going to form how many? Let's draw first and then I'll explain you. Yes. See students, 3p and 3p, that means 6 orbitals basically are combining. So 6 molecular orbitals will be formed. Initial one will be which? Sigma 2pz. It has a lower energy than the pi 2px and pi 2py. This is in the case when we have electrons more than 14. So this is basically your sigma 2pz. Yes. After that, students, what are we going to do? These are the two orbitals. This is pi 2px is equal to pi 2py. And then we have pi star 2px. This is pi star 2px is equivalent to pi star 2py. And at last, what do we have? At last, we have sigma star 2pz. So if you have to learn it, it is 1, 2, 2, 1. 1, 2, 2, 1. In the previous case, it was 1, 2, 1, 2. Yeah. Now, we have to fill electrons. Let's start filling the electrons. In 1s, we have 2 electrons of one oxygen atom. Now, in sigma 1s, we have 2 electrons. In sigma star 1s, we again have 2 electrons. Clear? Let's take another color. I don't know whether it's visible or not. In 2s, we have 2 electrons again. In 2s, we have 2 electrons. In sigma 2s, we have 2 electrons. In sigma star 2s, we have 2 electrons. Now, see, we have in P how many? 4, 4 we have already represented. In sigma 2pz, we have 2 electrons. In pi 2px and pi 2py, again we have 2 electrons. Now, in pi star 2px and pi star 2py, we have only one electron. So, this is the energy level diagram where here energy and here is orbitals. We have created for the case of O2. For the case of O2. Everybody just take a minute and write this down. Everybody, yes, just take a minute and write this down so that we can move on to the next part. Just take a minute and write this down, everyone. Shall we move now to the next part, everybody? Okay, students, now I will let you know how this sigma, sigma star, pi, pi star is created. Let's understand this. See, let's understand the formation of linear combination of atomic orbitals. Linear combination of atomic orbitals. Let's understand this now, students. See, if I am combining 1s and 1s, and both of them have positive and positive part. Now, what is this positive, negative? Representing the wave functions, you already know. See, when two positive are combining with each other, it will be a constructive interference. What they will do? They will create like this. So this is basically a constructive interference. This is when, if you'll see the overlapping is like this. You say sigma bond is created. Yes. Over here, when it is a positive and a positive both combining with each other, it is a constructive one. And in a constructive one, you are going to obtain sigma bond. And this basically is your bonding molecular orbital. In the case of constructive, we always obtain bonding molecular orbital. In the case of destructive, we always obtain anti-bonding molecular orbital. Let's take a case of destructive one now. If I have this again 1s and again I have this 1s, but over here it has a positive, it has a negative. When a positive and negative combines, it creates a destructive one. And when it will create a destructive one, they won't combine with each other. It will be somewhat like this. This will be positive, this will be negative. And there is some space over here. This space is basically, this line basically represents your nodal plane. Nodal plane is that region in which the probability of finding an electron is 0. And here if you'll see, electrons are clouded in such a way that it creates a spherical shape. Okay, here electrons are distributed, but over here only electrons are found over here, not over here. So this is nodal plane. This is destructive interference. This is the creation of sigma star orbital. Sigma star orbital, which is anti-bonding molecular orbital. AMO or ABMO, anti-bonding molecular orbital. Clear? This is the case of constructive one. This positive and negative symbol represents your wave function. Clear, everybody? Yes. Let's do with the case of now p orbitals. This was the S1. Now we are taking a case of p orbitals. Let us consider a case where we have now what? We are combining. Now which cases? See. This is your negative, this is your positive, this is your positive, this is your negative. I am taking this case when positive and positive poles are coming towards each other. An axial bond is created. How an axial bond is created? How will an axial bond be created? Basically, what will happen? This inner more region will be larger and the outer more regions will be smaller. This will become smaller and this center one will become larger. This is positive, this is negative, negative respectively. Right? So this is again the creation of a bond. If you'll see the overlapping region, you basically know this is a kind of overlapping that we obtain, right? So this region, in general, it is a larger one and these end one becomes the smaller one. So this is again the creation of which kind of a bond? Sigma bond. Why? Because this is again an overlapping like this. Axial overlapping leads to the formation of sigma bond. And this shows you the bonding molecular orbital. This is the constructive one. Let's talk about now the destructive case. Here we have positive, here we have negative. Now here we have positive and negative. Now see, positive and negative again, when they'll combine with each other, how they're going to create? Such kind of a bond is created. Such kind of a bond is created. Is it clear? Such kind of a bond is created. Everybody? No, this is wrong. Why? Let me show you how. Many of you will do this just as we have done this, but let me tell you, this is axial overlapping. This is not axial one. So let me explain you how you have to do is. See, over here we have seen when we are combining, the centermost region becomes the larger one and the smaller ones become, and the corner one becomes the smaller. Same will happen in this case. When you are combining both of them, it will lead to creation like this. This is positive, this is negative, this is positive. Getting my point? You will create these orbitals. This is the formation. And this is again the sigma star, anti-bonding molecular orbital. Clear, everybody? Next part. This was about axial. Let's talk about sideways overlapping. If we have it like this, let's say we have it like this, positive, negative, positive, negative. Again, the constructive one, if you are combining it all together in a constructive, it is going to be like this. This is complete positive, complete negative. This is formation of pi molecular orbital, which is basically like this. Electron clouds in general is like this. Why? Because see, if you will combine both of them together, do you remember the overlapping, how pi bond is created? There are two overlapping regions. So again, you have these regions as like this. This is formation of bonding molecular orbital. But if you are going with the destructive case, here is positive, here is negative, and you are combining with negative and a positive, you are going to obtain the one which I have drawn over here, like this. Positive, negative, negative, positive. This is the nodal plane. This is pi star, that is anti-bonding molecular orbital. Everybody write down. Now you know how constructive bond is created and how a destructive bond is created. Clear everyone? Just write it down, students. Shall we move on to the next part? Okay, now let's talk about the stability, students. Let's talk about the factors. The initial topic that we are going to do is stability. See, always remember the molecule that will become stable who has the bonding electron, number of bonding electrons more in comparison to the anti-bonding. So if number of bonding electrons are more than the number of anti-bonding, that is stable. That is stable. If number of bonding is less than number of anti-bonding or it is equal to anti-bonding electrons, it is unstable. Now you will say, ma'am, how we are going to calculate bonding one and the anti-bonding one? This NB represents number of bonding electrons, Na represent number of anti-bonding electrons. Many of you will say, ma'am, how we are going to calculate it? See over here. The ones with only sigma, sigma, there is no star, that is bonding one. The one which contains a star, that is anti-bonding. So this is 2 plus 2, then 2, 2, 2, this is bonding. What is anti-bonding? Star 1, star 1, star 1, star 1. Count the number of electrons over here, you will get the anti-bonding one. So if they have the value, number of bonding have the value more than the anti-bonding one, they are the stable. If they have a lesser value, they becomes unstable. This is the very first initial factor that you should know, students. You should know, students. Clear? Now let's talk about the bond order. How you have to calculate the bond order, students. What basically is the bond order? Bond order basically determines number of bonds created. Let's read the definition. Bond order is defined as one half of the difference between the number of electron present in bonding and the anti-bonding. Basically, it represents number of the bonds created. How you have to calculate? Bond order is basically half of number of bonding electrons minus number of anti-bonding electrons. This is the formula for the case of bond order. For the case of bond order. So if I'll ask you what is the bond order of N2, how you're going to calculate? You have to put the value of the number of bonding electrons, then subtract the value of number of anti-bonding and divide it by 2. Basically, for that you have to write electronic configuration, which I have already explained you. Clear everyone with this part? Everybody write it down. Write this down. And one more thing, one more factor. See, if let's talk about bond length. See, students, always remember, more the bond order, lesser is the bond length. So this is the one thing that you should know, that bond length is basically inversely proportional to bond order. Do remember this part also. Clear everybody? Write this down, students. Done. Let's talk about the last factor, that is magnetic behavior. Let's talk about the last factor, that is magnetic behavior. See, if it contains any unpaired electrons, it is paramagnetic in nature. And if it contains any paired electrons, no unpaired electrons, it is diamagnetic. And how to calculate the magnetic moment? It is basically mu is equivalent to root n plus 2 Bohr magneton, where n represents number of unpaired electrons. Number of unpaired electrons. Clear everybody? This was about molecular orbital theory, and hence we complete our topic of molecular orbital theory over here only. Let's start with now the limitations of octet rule, students. Molecular orbital theory part has been completed. Now proceeding towards the topic that are left over. Octet rule I've already explained you. When an element completes its octet rule, that means it should have a maximum 8 electrons in the outermost shell. Yes, there are exceptions of duplet of hydrogen and helium. Hydrogen should have to complete the duplet, and helium also is basically completing its duplet. That means it has 2 electrons in the outermost shell. Rest the complete should have 8 electrons in the outermost shell. But there are some limitations due to which octet rule failed out. The very first was incomplete octet of the central atom. It was seen that the central atom does not contain the 8 electrons. Let us take a case of BeCl2 if I'll talk about. If you'll see the formation of BeCl2, beryllium basically holds an atomic number 4. So electronic configuration is 1 is to 2 is 2. That means if you have to show the Lewis dot representation, it will show only 2 electrons. Why? Because in 2s orbital it has 2 electron. Outermost shell it has 2 electron. Chlorine basically has 7 electrons. So we are going to represent it like this: 1, 2, 3, 4, 5, 6 and 7. Similarly, another chlorine also holds 7 electrons. So it will be represented like this. Now see students. Basically, chlorine gets 1 electron of beryllium, and over here also so it completes its 8 electron. 1, 2, 3, 4, 5, 6, 7 and 8. 1, 2, 3, 4, 5, 6, 7 and 8. But if I talk about beryllium, see how many electrons in beryllium? 1, 2, 3, 4. 4 electrons. It should have complete 8 electrons, but it is completing 4 electrons, which is an incomplete octet. So basically, it completes an incomplete octet over here. Hence, this rule failed out. There are many examples if you can take from NCRT in the incomplete octet. Next is odd electron molecules. Now there are some cases such as, if I'll take the case of NO2, if I'll take the case of NO, in both of the cases, nitrogen holds the odd electrons. If you'll calculate the value of total electrons also, the value comes out to be an odd number, not an even number. So this is again an exception, right? Because octet rule is 8. 8 is even. They are containing odd number. That means it is again a limitation of the octet rule. So in molecules with an odd number of electron like nitric oxide and nitrogen dioxide, octet rule is not satisfied for the atoms. Now in the next part, the expanded octet or the super octet or the hypervalent. See, when we have lesser number than the 8, that is hypovalent. When we have a more than 8 electrons central metal hold, that is hypervalent. That is expanded octet. Example you can take is of PCl5. See, phosphorus basically, contains 5 electrons in the outermost shell, no? How many electrons, ma'am? 5. 1, 2, 3, 4 and 5. Yeah? Now see, chlorine basically holds 7 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6 and 7. Now see over here students. Chlorine basically is acquiring 1 electron of phosphorus, another electron like this. Let's count the electrons for phosphorus now. See. 1, 2, 3, 4, 5, 6, 7 and 9, 10. Phosphorus holds 10 electrons. Central metal atom has more than 8 electrons. So it is again a limitation. Similarly, you can take the case of IF7, SF6, H2SO4. All of these cases, central metal holds more than 8 electrons. So again, this is a limitation for the octet rule. Next limitation is Lewis octet rule gave no idea about the shape and the geometry. And one more limitation was that it had no idea. It said that inert gases cannot create compounds. But yes, we have seen they are creating compound. XUF2, right? We have seen many cases. In the upcoming examples also, you are going to see compounds with xenon. So inert gases do create compounds. But according to octet rule, they cannot create. Right, because it is already 8 electrons. Let's read more drawbacks from the NCRT with regard to octet rule. It is clear that octet rule is based upon the chemical inertness of noble gases. See, this is what I have told you, right? They told that they are inert in nature, they cannot create any compound. Some noble gases, for example, xenon and krypton, but they combine with oxygen and fluorine, such as XeF2, KrF2, XeOF2. So they have created. This is again a drawback. Next, this theory does not account for the shape of molecules. It won't, explain about shape and geometry. So this failed out. Next, it does not explain about the relative stability of the molecules, being totally silent about the energy of a molecule. So it does not explain about that as well. Moving on to the next topic, students. Now we have about lattice energy. What do you refer to as lattice energy, students? Let's read this from the NCRT highlight. But before that, let me explain you what is lattice energy. See, basically, amount of energy, if I say required to create a bond, at that amount of time, energy released is lattice energy. Or amount of energy required to break a bond, that is lattice energy. Energy released when a bond is created or energy absorbed in order to break a bond is lattice energy. So what is lattice energy? Is defined as energy required to completely separate one mole of a solid ionic compound into its gaseous constituent ions to break it out. For example, lattice energy of NaCl they have given you. This means 788 kilojoule of energy is required to separate one mole of NaCl into Na positive and Cl negative. This process involves both the attractive forces between the ions of opposite charges and the repulsive forces. That means lattice energy depends upon the interactive forces. There are various factors on which lattice energy depends. I'm going to tell you the factors, but before that, everybody do write this down so that we can write down the factors for the lattice energy now. Yes, students, please write down each and every part over here so that we can now write down the steps for the factors. Yeah, shall we? Now, the very first factor is charge. Lattice energy depends upon the charge. More the charge, students, more will be the lattice energy. Why? Because more the charge, more will be the electrostatic force of attraction they will be having. So you have to provide a high amount of energy. So more is lattice energy. If I'll talk about size, lattice energy and size are inversely proportional. You know, higher is the size, lesser is the lattice energy. Smaller the size, greater the attraction, higher is the lattice energy. So it is also dependent upon the size. So yes, these are the factors, that is charge and the size, that affects the lattice energy. Everybody do write this down. And yes, lattice energy is directly proportional to stability. So more the lattice energy, more will be the stability and more will be the melting point. Students, it is also going to affect the solubility, but yes, this order is enough. I'm not saying solubility will increase or decrease. I'm just telling that it will affect this as well. So more the lattice energy, more will be the stability, more will be the melting point. Everybody write this down. Now we are going to start with the bond parameters, everybody. We are going to start with the bond parameters, right? The very first bond parameter is bond angle. Bond angle. What is the bond angle? An angle created when, when the bonds are connected with each other, right? When we see in a molecule bonds are created, so the angle between two bonds is bond angle. It is defined as angle between the orbitals containing bonding electron pairs around the central metal atom in a molecule or a complex ion. It is expressed in degree, which can be experimentally determined by spectroscopic method. It gives us some idea regarding the distribution of orbital around the central metal atom. Okay, example, in the case of water molecules, okay, it can be represented in such a way, right? For example, in I3 negative, we create a 180-degree bond angle, a linear shape. In BeCl2, we have a linear shape, 180-degree angle. In tetrahedral, we can determine the bond angle, the angle between the two bonds, right? But yes, there are some factors that affect the bond angle, the hybridization also, students. That is about Drago's rule. Let's discuss about Drago's rule. In Drago's rule, what happened is, this is applied for the group number 15th, 16th, 17th. Now, what happens in the case of Drago's rule? It is not applied on the first element. It is applied on the second elements. From the second elements. That means from phosphorus, if I'll talk about, from sulfur, if I'll talk about, from chlorine, if I'll talk about. This starts from that. Basically, just leaving the case of nitrogen, oxygen and fluorine above, rest of the molecules have almost 90-degree bond angle. Almost 90-degree bond angle with no hybridization. Why? Because their pure, orbitals are combining over there. Okay, pure orbitals are combining. Now, basically, in the case of nitrogen, oxygen and fluorine, why it is not happening? Because they have a smaller size. So, from the second elements, that means phosphorus, sulfur and chlorine, the bond angle, if you'll see, is almost 90-degree. One of them will have 91, 92, nearly 90-degree, right? And they have no hybridization. Only the nitrogen, or I would say the oxygen and the fluorine atoms will have certain hybridization and a certain bond angle, right? Clear, everybody, students? Now let us move on with bond enthalpy. What is bond enthalpy? Bond enthalpy, in other terms, is basically I've already told you about bond enthalpy, that it is directly, it is inversely proportional to the bond order. Yes. So let's read about it as well. It is defined as amount of energy required to break 1 mole of bond of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole, and we have already read that bond enthalpy basically is inversely proportional to bond order. More the bond order, lesser is the bond enthalpy, right? Because see what happens is, if you'll see, when there is a single bond, it has a higher bond enthalpy in comparison to the triple bond. Triple bond is basically, if you'll see in the case of triple bond, what happens is, no, let's understand this in depth. For example, if you have a single bond, only one hand is holding another atom. If we have three bonds, three hands are holding it, there is a greater force of attraction, lesser the size is smaller, greater will be the bond enthalpy. So you have to understand this in terms of the bond created over there. Clear, everybody? Just write down for the bond enthalpy. That bond enthalpy, sorry students, just correct it over here. Just correct it over here. You can understand this by the case that bond, sorry, this was about bond length, no? Greater the bond length, greater the bond length, greater the bond order, lesser is the bond length. This is right. But over here, if I'm telling about bond order, yeah, bond enthalpy, I don't know whether I've written for bond enthalpy or not over here. I was just checking that page. Just give me a minute. This is about lattice energy, bond length, magnetic behavior, bond order. No, we have not written about it. We are going to write it over here. Just understand what I've told you. I told you more the bond order. Now, what is bond order? The bonds between them. More the bond order, what will happen? If it is a greater bond order, size will become short, right? Because, for example, if I single hand, a single bond holding another atom, okay, and now I have three bonds holding the another atom. Three bonds holding, so force of attraction will be stronger, size will be smaller. If size is smaller, you have to provide a lot of energy because the force of attraction will be greater, attraction force will be greater. Hence, you have to provide a lot of energy, so bond enthalpy is greater. So bond enthalpy is directly proportional to bond order, but yes, bond length is inversely proportional to bond order. Don't get confused. Next part, it is directly proportional to electronegativity also. If you see bond enthalpy is greater, size is smaller. So bond enthalpy is inversely proportional to size. Clear, everybody? Do remember these factors over here. Do remember these factors. So now comes about bond order. We have already studied, but let's read about it. In the Lewis description of covalent bond, the bond order is given by the number of bonds between two atoms in a molecule. Number of bonds between two atoms, right? Now, the bond order in the case of H2 with a single shared electron pair. In O2, we have two shared electron pairs. In N2, we have three bonds in N2, right? 1, 2, and 3 respectively will be the bond order. So, they have given you, even you can calculate with the formula, half into number of bonding minus number of anti-bonding electrons. Clear, everybody? Now, students, comes the dipole moment. Dipole moment, basically, you have studied in your physics also. But over here, let me tell you about dipole moment in detail. How you can explain about dipole moment? See, dipole moment you can do when you are seeing the atom from less electronegative atom to the more electronegative atom. This is direction. How you can depict the direction from less electronegative atom to the more electronegative atom, or from atom to lone pair. By this way, you can calculate the dipole moment. You will be provided any molecule, just put the arrows. Just put the arrows, you will get your answer. Let's take a general example over here, students. So students, as I have told you that we have to see the direction, let's take some case of BeCl2. So BeCl2 has a linear shape. Now we have to move in which direction? From lesser electronegative atom to the more, less to more, less to more. Now they are cancelling each other, so the dipole moment is 0. Let's take one more case of SO3. Now see in this case, now oxygen is more electronegative because in oxygen family, as you're moving from top to bottom, electronegativity decreases because size is basically increasing. So the directions is like this. Now it is going in upward direction, both are going over here, so the resultant is like this, one upward, one downward, again it is cancelling. Dipole moment is 0. In such a way you can calculate dipole moment. These are the ways, these are the directions provided how you have to create these lines. From lesser electronegative atom to the more one, from atom to the lone pair. Clear, everybody? Now students, let's start with the hydrogen bonding. What is hydrogen bonding? Hydrogen bonding basically is a bond that is created between hydrogen of one molecule with more electronegative atom of the another molecule. Now that more electronegative atom can either be fluorine, oxygen, or nitrogen. Now many of the students think that, ma'am, why not chlorine? Chlorine has an electronegativity almost similar to nitrogen. Why not chlorine? Because chlorine size is the bigger size. Do remember that one thing you need to keep in your mind. There are some conditions in order to exhibit hydrogen bonding. The very first condition is that hydrogen creating a bond with another atom's more electronegative atom, that more electronegative atom should contain lone pair of electron. Second thing, hydrogen which is creating a bond with the electronegative atom, that hydrogen should be covalently attached to a molecule which has a smaller size. Then only hydrogen bonded will be created. Few examples over here is, for example, we have this HF, HF, HF over here. Now see, hydrogen basically carries partial positive, fluorine partial negative, partial positive, partial negative, partial positive, partial negative. So basically hydrogen of this molecule is creating a bond with the fluorine. This is hydrogen bonding. Hydrogen creating a bond with this is hydrogen bonding. The dotted one is hydrogen bonding. The solid lines is covalent bonds. So the covalent atom over here, fluorine atom over here should have a smaller size. Clear? Basically this hydrogen created a bond with this should have a smaller size, this should contain a low number of electrons. Let's take the case of water. Now see, hydrogen creating a bond with more electronegative atom. Clear everybody? This is what is hydrogen bonding. Now there are two types of hydrogen bonding, intermolecular and intramolecular. Everybody first of all write it down. Then we shall be proceeding towards the types of hydrogen bonding. Everybody just write it down. The very first is intermolecular hydrogen bonding. Students, that exist between two molecules. The hydrogen bonding that exists between two molecules. For example, now only I have told you HF, HF. The hydrogen bonding between two molecules. That is intermolecular hydrogen bonding. Clear? What is intramolecular? Intramolecular is between a single molecule but between different groups. Between a single molecule but between different groups. For example, I have this orthonitrophenol. Orthonitrophenol. Let us take this case. I have this orthonitrophenol. Can I write it like this? So over here you can clearly see that a ring like structure will be created. How, ma'am? Which is basically creating a bond. Hydrogen is basically creating a bond with what one? With oxygen. Right? So this is a ring like structure being formed over here. This is basically called chelation also. Intramolecular hydrogen bonding between one molecule, between different groups. Clear everybody? Clear everybody? Okay. Now let's move on to the last topic that comes out to be Fazan's rule. These students, in Fazan's rule, basically it is, covalent character present in ionic bond. Let's understand about it. Now basically this is attraction of distortion of electrons, okay, of anions towards cations. This is what is Fazan's rule. Let's understand this. For example, if this is a cation and this is an anion. Now what happens is, anions basically get attracted towards cation. So what is seen that they basically, when they're moving towards cation, they basically distort their shape. And when they're distorting their shape, it seems to be that there is sharing of electrons. When it is moving towards it basically distorts its original shape, due to which it seems to be that they are sharing electrons, but in actual they are not sharing electrons. This is just a force of attraction. So it's when there is sharing of electron, that is covalent character. It seems to observe a covalent character, but in actual it is not a covalent character. In actual it is attraction, right? So this is basically what is distortion of anion towards cation is referred to as your Fazan's rule. Now basically on which factors do they depend, right? Always remember, small cation, okay, and larger anion, small cation, larger anion and high charge will lead to a good covalent character, will have a good covalent character. So whensoever they'll give you some options of the covalent character, always see the cation size. If it is smaller, it will have a good covalent character. If it has a high charge, it has a good covalent character. Right, students? So now, students, we are going to end our today's class over here. I hope so today's session was helpful for you. We have completed the whole chemical bonding in this particular sessions, 8 lectures. I hope so it was clear to you, students. Now it's time for you to practice questions. And now it's time to move on to the physical chemistry fifth chapter, that is states of matter, which sir will be holding. So we will be meeting after physical chemistry again with inorganic chemistry. I hope so both the chapters, periodic classification of elements, and this one, chemical bonding, was clear to you, students. Now we shall be meeting in the next class. Till then, keep smiling, keep learning. Thank you so much and have a good day, everybody. Take care of yourself. Thank you.